So this question is also from the front page of that acceleration worksheet on angular acceleration and tangential acceleration in this particular section. Okay, it reads, in 1986 in Japan, a giant top with a radius of 1.3 meters was spun. The top remained spinning for over an hour. Suppose the people accelerated the top from rest so that in the first turn, it was completed in 1.8 seconds. What was a tangential acceleration of the point on the top rim, or just the top rim in general? Okay, so here we are trying to find tangential acceleration, or AT. Okay, there's only one formula on that entire formula sheet that lets you solve for tangential acceleration, which is AT is equal to AR times the radius. Okay, we've been given the radius of the top, which is 1.3 meters, but we don't have the angular acceleration, so that's what we're going to need to find first. But again, there are a ton of formulas on the formula sheet that allow you to solve for acceleration, so let's look at what other variables we have so that we can select the correct one. So the top remained spinning for over an hour. That gives us a little bit of information about time, but this is not specific enough. It doesn't actually tell us a time period or any variables for that over an hour time period. So we're going to move on to the second sentence that says, suppose these people accelerated the top from rest. So we know at the beginning of the time period, the initial speed was 0 radians per second. And during that acceleration, it completed one turn in 1.8 seconds. So we also know the angular displacement of that same time period, and we know the amount of time that it occurred in. So angular displacement is 1 revolution, okay, and time is 1.8 seconds. The only problem is that angular displacement shouldn't be in revolutions, it should be in radians. So I'm going to multiply this by 2 pi radians per 1 revolution. So my angular displacement is 2 pi radians. And again, I'm not going to calculate that out just yet because I want to plug this whole number in without having to worry about conserving decimal places. So I'm going to leave that as is right now. So essentially, I've been given the initial speed, the radius, the angular displacement, and the time for one particular interval, and I need to use that to find the angular acceleration. There is a formula on the formula sheet that allows you to do that, and that formula sheet is theta is equal to the initial time, or the initial speed times time, plus 1/2 of the acceleration times time squared. Okay, so again, I'm trying to solve for this angular acceleration, so I need to rearrange that formula in order to solve for AR. So I start with theta minus the initial speed times time is equal to 1/2 acceleration times time squared. Okay, then I'm going to move that half over, or cancel the half out on both sides. So I end up with 2 theta minus the initial speed times time is equal to acceleration times time squared. And then I just need to move over that time squared. So I'm going to divide both sides by time squared. Which should give me the angular acceleration for that moment in time. Okay, if I plug those numbers into my calculator, you should end up with an angular acceleration of approximately 3.87 radians per second squared. Okay, and now that we have the angular acceleration and we have the radius, we can multiply those two terms together to get a tangential acceleration, which is 5 meters per second squared. Okay, so again, this one's just about identifying the period of time where the acceleration was occurring. Okay, writing down all the variables you have for that specific period of time. So we know the initial speed for that period of time. We know how far the top rotates during that period of time, and we know that the time it takes. Then you look at your kinematics formulas and find the one that contains all of those variables, including angular acceleration. Then you rearrange the formula to solve for angular acceleration, and then using the angular acceleration and radius, you can find the tangential acceleration.